Hi everyone. In this video, I'm going to talk about basic Poisson regression for count data, and I will give an example to illustrate how to do the R coding. Our goal here is to first understand what is generalized linear models, GLM, for count data under Poisson regression, and how do we interpret the beta. The example I'm going to show here is called Horseshoe crabs and satellites, which is a very classic one. And I will also show my R coding to help you understand how did I test general hypothesis about Poisson GLM parameters. So first, to understand what is GLM for count data, we have to make sure two conditions are fulfilled. One, the count of possible outcomes, which is also our response variable y, are non-negative integers. Two, generalized linear models for counts have as its random component Poisson distribution. For example, if we want to know the number of violent incidents exhibited over a 6-month period by patients who had been treated in the ER of a psychiatric hospital, this is a type of problem that we might encounter for count data, and we can use GLM to solve it. For a Poisson regression for counts, our response variable is a count, and our explanatory variables have two conditions. First, if they're all categorical, for example, you have a contingency table with counts in the cells, we convert this into a log linear model. Second, if they're numerical or continuous, we convert it to a Poisson regression. Note here, in this video, we only talk about count data, but when the response variable divided by time t, it can also be called the rate, which is another condition. So the Poisson distribution has a positive mean. GLMs for the Poisson mean can use the identity link, but it's more common to model the log of the mean, like the linear predictor alpha plus beta x. The log of the mean can take any real number value. A Poisson log linear model is a GLM that assumes a Poisson distribution for y and uses the log link function. For a single explanatory variable x, the Poisson log linear model has the form log mu equals to alpha plus beta x. The mean satisfies the exponential relationship here, so min mu equals to exponential x plus alpha plus beta x. So we interpret beta as a 1 unit increase in x has a multiplicative impact of e to the beta on mu. The mean of y at x plus 1 equals the mean of y at x multiplied by e to the beta. So if beta equals to 0, then e to the beta equals to e to the 0 equals to 1, and the multiplicative factor is 1. So the mean of y does not change as x changes. If beta greater than 0, then e to the beta greater than 1, and the mean of y increases as x increases. If beta less than 0, the mean decreases as x increases. Let's have a look at our data on the example horseshoe crabs and satellites. First, our data frame is 173 observations on the following 5 variables, including the female crab's color, spine condition, weight, and carapace width. Each female horseshoe crab in the study had a male crab attached to her in her nest. The study investigated factors that affect whether the female crab had any other males called satellites residing nearby her. The response outcome for each female crab is her number of satellites, and in this example, we consider carapace width as the only predictor of the number of satellites residing nearby the female crab. Now let's have a look at my R code. First, we read the table and then we attach the data. The first thing I do is trying to plot a scatter plot. between the V's and the number of satellites to see if there is a clearly pattern. And the graph here shows there's no any particular pattern, so a more informative plot can be constructed. What I did here is I create a grouped version of data by dividing the female crab's width into 8 width categories. So after I group the data here, it looks like this. And now I plot a new plot after I group the data. Now you can see a clearly increasing trend on this graph. And here I use a t-apply function, which applies a function, in this case is the mean and variance functions, to a variable, the number of satellites, after the mean number of satellites after grouping the width of female crabs. And the next thing I'm going to do is just to use GLM function to do the regression, Poisson regression. So, and I summary the model. I will get the number for betas, and I will get my word test z squared, word test z equals to 8.216 with p-value very small. So note here, for Poisson family, the log link is the default setting here for the GLM. And according to the summary table here, we can actually calculate by hand for the chi-square statistic. It's just the differences between the deviances divided by the degree of freedom. But a better way to get the likelihood ratio test, the chi-square, is to use the ANOVA. So the ANOVA function here will get the chi-square statistics with a very small p-value here. So according to the summary table, our conclusion is the log linear function looks like log hat mu equals to negative 3.30476 plus 0.16405 times x, and the word test statistic z equals to 8.126, and the associated p-value here is close to 0, which is highly significant. Thus, we conclude that there's a significant, which is also like a positive, linear association between number of satellites and the width of carapace under our null hypothesis, which is beta equals to 0. And also the ANOVA has a very, very small p-value too, so we have the same conclusion here. And now we can get a predicted count for each observation, and it looks like this. So for the first response, y1, we get the predicted value equals to 3.181, which is just by the formula e to the beta here. And now we can simply predict a new value with our model. So if our width, the mean carapace width is 26.3 centimeter, we obtain our fitted value mu hat, which equals to e to the negative 3.30476 plus 0.16405 times 26.3 equals to 2.744581. So based on the fitted GLM, our best estimate of the number of satellites for a crab with width 26.3 centimeter is 3. And also from this model, we can see like e to the beta hat, which beta hat equals to 0.16405, equals to 1.18, which means a 1 centimeter increase in carapace width yields an 18% increase in the estimated mean number of satellites. And for more diagnostic measures, we use the influence method here. So the influence actually is the residues function will extract the unadjusted Poisson or chi-square and deviance residues, the default from a fitted GLM object, and there seems to be no built-in function for computing the adjusted or standard residues. But the influence will extract the diagonal of the so-called hat matrix, and this is enough to construct the adjusted residues. So we run this. We will get our graph, but this shows that it's not equally distributed around 1 or 0, so it's not a good fit. And we can also test the Poisson chi-square test, on which equals to 0 is also not good. So the both test results indicates lack of fit of the model. And now let's assume we do not have other covariates, and we will adjust for over-dispersion. So the over-dispersion means count data often vary more than we would expect if the response distribution truly were Poisson. For instance, for the grouped horseshoe crab data here, we have the sample mean and variance for the counts of the number of satellites for the female crabs in each width category that we already show you here in the beginning. Okay, we'll just run it again. Oh, here. That's the graph here, and so by looking at the table, we can see the variance are much larger than the means, whereas Poisson distribution should have identical mean and variance. So this phenomenon of the data having greater variability than expected for a GLM is called the over-dispersion. And for the over-dispersion, we use the disperse GLM function here. And another way to do this adjustment is to fit a negative binomial model with the dispersion parameter theta. But for this method, we have to use library math. And we will get this after adjustment. Okay. So here is the summary result for our example horseshoe crabs and satellites. We will get our fitted model, and we conclude there is a significant positive linear association between number of satellites and the width of carapace. Also, we can calculate the estimated number of satellites using our fitted model and the interpretation of beta. So if you're interested in more, you can just Google horseshoe crabs and satellites. There are a lot of tutorial materials online. And for the over dispersion part, I didn't explain well because I don't understand that really well. And I need to study that too. And hope you enjoyed the video. Thank you guys for watching.